Alrighty, so the next section we want to consider is the reality of the error that exists in any of the measurements we make as scientists. We go into the laboratory and we use a balance or a piece of glassware such as a volumetric pipette, and we make measurements of mass or volume, etc. All of those measured values have some degree of error or uncertainty with that measurement. So this limits the confidence we have in that value. And so we do not want to ever over-interpret our confidence with our measured values. So with this in mind, we want to always be cognizant of the uncertainty with the measurements we make in the laboratory. Okay, so we use a lot of different instruments, and some are going to give us a higher degree of confidence and others less. So we represent our confidence by the last digit in the measured value. Okay, so let's consider the following scenario. We have a lake and we are concerned about the concentration of lead in the lake. And so we're going to collect a water sample. And we're going to use some method of analysis to determine the concentration of the lead in that water sample. So the Environmental Protection Agency has established toxicity for heavy metals such as lead. And it is recognized that lead is toxic to humans if consumed when the lead is greater than a concentration of 10 parts per billion. Okay, so we go to the laboratory and we use a particular method, such as maybe atomic absorption spectroscopy, and we determine that the concentration of the lead is 9.7, but the uncertainty in our measurement is 0.5 parts per billion. So we are uncertain about the value of the last digit in the number that we obtain. So there's uncertainty in that first decimal place. Okay, so what do we really know about this measured value with that degree of uncertainty? So we know it to be 9.7 plus or minus 0.5. So all I really know is that the concentration of lead is somewhere in a range, okay? A range of 9.7 minus 0.5 to 9.7 plus 0.5. That is all I can confidently interpret from this value. So all I really know is it's somewhere between 9.2 and 10.2 parts per billion. So with that measurement, I cannot, with a high degree of certainty, make any interpretations that this water sample is not toxic, in which the toxicity level is 10 parts per billion. It certainly could be. It may not be, but it could be. All right, so contrast this with making that same analysis with a different method that delivers to us a higher degree of certainty in our measurement. So let's say that using our second method, maybe inductively coupled plasma mass spectrometry, we determine that the water sample is 9.70 plus or minus 0.05 parts per billion. So now what I know is that the sample is somewhere in the range of 9.65 to 9.75 parts per billion. So with this measurement, I have a high degree of certainty that the sample is not toxic at 10 parts per billion. So this is a huge distinction, and it's all owing to the uncertainty in these values. Okay, now that we recognize the importance of the uncertainty in our measurements, we need to delve further into the possible sources of error. And so basically error comes from one of two places. First, accuracy is a measure of the closeness of our measured value, which does have uncertainty in it. Okay, it's how close that value is to what we call the true value, the known value of that measurement. And we're going to substitute the symbol x subscript t for the true value. Okay, so some ways we measure accuracy. Absolute error is the difference in the measured value x and the true value x sub t. Relative error is going to be that difference in those two numbers divided by the value of the true value, x sub t. That makes it relative. And then percent relative error is simply 100 times the quantity of the relative error. So it's symbols percent RE, so it's going to be 100 times the quantity of the difference of the measured and true value divided by the true value quantity. Okay, the other source of uncertainty is precision. Okay, this is the agreement of measured values. We do multiple measurements, and it's the agreement of those repeated measurements in which we used exactly the same procedures in collecting that data. So another word for precision is reproducibility. Can we reproduce the experiment and come up with the same data? Okay, and the measures of precision, one is a statistical measure known as standard deviation, and we abbreviate that typically with a small s and a small d. Okay, all right, so where precision comes from, if we have multiple experiments, we make multiple measurements, such as the data collected here, 4, 2, and 3, and we apply statistics, okay? The mean or the average value is the sum of all of our data, our x values, divided by the number of experiments, in this case 3. So if you add 4, 2, and 3, that's 6 and 3 is 9 divided by 3, so our average value is 3. Okay, then we can calculate through statistics something called a standard deviation. And I will let you explore on your own how one goes about calculating standard deviation. Okay, for this data set, the value of the standard deviation should come out to be 1. Okay, therefore, when we report the mean plus or minus the standard deviation, this would be 3 plus or minus a value of 1, the 1 representing the standard deviation. And one note about precision, the sources are random and we cannot correct for them. Okay, there's variability in the data. Okay, so let's put the concepts of accuracy and precision in measurements to work. So we're going to look at a set of data. The data was derived from analyzing samples using 3 different methods. And those 3 different methods, we're going to repeat the measurement 3 times for each of those 3 methods. And so I'm going to compile that data into a table below. And then once we have the data, we're going to look at the values for the mean, the average, and the standard deviation to assess which method yields the best and the worst accuracy and precision. Okay, so here's our data. We have all kinds of tools, instrumentation available to us as chemists to analyze samples. So I'm just going to give you some theoretical data using 3 different instrumental methods of analysis. And we are going to repeat our measurement 3 times for each of those methods. Method 1 delivers a value of 25, 18, and 20. Method 2, 26, 28, and 27, and method 3, 22, 20, and 21. So I'm going to use statistics, and I'm going to calculate the mean, the average value first, and then the standard deviation. So the first method gives me 21 plus or minus 4, second 27 plus or minus 1, and the third 21 plus or minus 1. So for this given sample, it is known that the true value is 21. So with that information, let's analyze each method for the quality of the accuracy and the precision. Method 1 delivers good accuracy, good agreement with the true value. However, the precision, not so great, plus or minus 4. And that's the standard deviation. Method 2 does not give us good accuracy. An average of 27 is far from the true value. But it does deliver good agreement between the measurements, and that is the standard deviation as indicated by 1. And finally, method 3, it gives us very good accuracy, good agreement with the true value, but it also delivers precision, a good agreement of the measured values. So this is the ideal scenario for a technique. We want both good accuracy and good precision, and that's going to give us more confidence in our measured values, and the measured values are going to be closer to the true value. Okay, it's time to give your brain a break. Here's a picture of Annie at her 11th birthday party. I don't know if she's learned to count yet, but she certainly knows that when the candles go out, she gets her favorite thing, ice cream. Okay, so we are on to the last section in your notes for this chapter, and that is significant figures. It's going to be very important as chemists that when we record data in the laboratory and we subject that data to calculations, we report final calculated values to the correct number of significant figures. We just reviewed why that's incredibly important. It indicates the confidence that we have in our data. Okay, so there's rules in how we determine the number of significant figures when we look at a number. So you look at the number and you start on the left side of the number, you read it left to right, and you start counting digits when you get to the first non-zero digit. So we're going to practice doing this for a couple of values so that we get back in the swing of things of determining the number of significant figures. So here's our first value, 0.0103, left to right. I don't count till I hit the 1, so there are 3 significant figures. 1.630, we start counting with the 1, so there are 4. And then 0.0074, you don't start counting till you get to the 7, so there are 2. All right, so lots of things we got to keep in mind regarding numbers, starting with whole numbers, and these can be tricky when we determine significant figures. Zeros to the left of the decimal may or may not be significant. So we have to be careful how we report those numbers to convey the correct number of significant figures. So let's look at such a number. Let you get the rest of these notes down. Okay. Once again, the zeros to the left of the decimal may or may not be significant. So we're going to look at the value of 8,700. Okay. We start counting with the 8. It's significant. The 7's significant. But those other 2 zeros may or may not be significant. So we could have 2, 3, or 4 significant figures. The only way we know for sure is to express this number in scientific notation. So, if this number were written as the following, 8.7 times 10 to the third, that's how we know there's only 2 significant figures. If it were written as 8.70 times 10 to the third, Now we know there's 3 significant figures. And finally, if it's written as 8.700 times 10 to the third, then we know the value has 4. And just a note, my notation there is wrong. That should indicate 4 significant figures. Okay, the next thing we need to be cognizant of is when we use conversion factors, those are exact numbers. An exact number is going to have an infinite number of significant figures. The point is these values will never limit the number of significant figures in your answer. So conversion factors are things like 12 inches is the equivalent of 1 foot. That has an infinite number of significant figures. When we're using molar masses from the periodic table, those numbers are known to a large number of significant figures. So we will always use enough so that we aren't limiting our answer by that value. So important thing to know later on when we get to using molar masses. So the important thing to recognize is when you're doing calculations, the sig figs in your answer is always going to be dictated by your measured values that have limited significant figures based upon the instrument and the degree of confidence we have in the values that we measure. Okay, so when we do mathematical functions, starting with addition and subtraction, okay, the rule on sig figs in terms of the sum or the difference is that we're going to be limited to whichever value had the fewest decimal places. Okay, so we're going to look at which value has the fewest decimal places, however many that is. We're going to apply that to our answer and then report the sig figs. So if I take the sum of 18.73, 1.2, and 4.318, that value is 24.248. My first number in the list has 2 decimal places. The second number, 1.2, has 1 decimal place, and the third has 3 decimal places. So the least decimal places is 1. So my answer, I'm going to truncate at the first decimal place. Report this is 24.2. Therefore, the overall number has 3 significant figures. Okay, next rule is if we're doing multiplication and division. It's a different rule. The number of sig figs in our answer is going to be limited by whichever value has the least number of significant figures. Okay, so we're going to do a calculation. Density is defined as mass per unit volume. We went to the laboratory and measured a mass of 39.6 grams. And we're going to divide by a volume of 1.047 cubic centimeters. So the numerator, the value 39.6, has 3 sig figs. The denominator, 1.047, has 4 sig figs. The dividend of these two is 37.8223. Units are grams per cubic centimeter. So my answer is limited to 3 sig figs. So counting left to right, that would be 37.8. And that is the density in units of grams per cubic centimeter. Okay, the next thing we just want to review real quickly are the rules we apply to rounding numbers. So hopefully none of this is new to you. If you've got a value such as 15.3942 and we find that the 9 is our last significant figure, okay, if the next value is less than or equal to 4, you drop it. So because the 4 is a 4, you drop it. Okay, 15.3963, if the 9 is the last sig fig, then because the next value is greater than or equal to 5, we round up. This would be 15.40. And then if the digit after our last sig fig is a 5 followed by something other than a 0, you're going to round up. So it's going to be reported as 15.40. Okay. Next thing we want to do are successive operations. Okay, what if we combine doing addition, subtraction, and multiplication and or division all in one big operation involving measured values and conversion factors and that kind of thing? So we're just doing math. So all the rules of math apply. So you do whatever function is in parentheses first, applying the appropriate rules, and then just be a good bookkeeper. Put a dash underneath the last sig fig, but the important thing is we do not round until the very end. So I'll show you what I'm talking about. So let's take 8.71 multiplied by 0.0301 and then divide by 0.056. Okay, we're doing both multiplication and division. Do what's in parentheses first. The rule is you're limited by whichever value has the least sig figs. Each of these values have 3, so the product has 3. And then in the denominator, we divide by 0.056. That value is limited to 2. So our answer is limited to 2. Okay, and the result is 4.6816. We are limited to 2 sig figs. We're going to round to 4.7. Okay, next one, we are going to take 934 and we're going to multiply by 0.00435. Once that's done, we're going to add to 107. First operation, well, the overall answer is 111.06. Okay, first operation is multiplication. We are limited by significant figures. The first value has 3, the second one has 3, therefore the product is limited to 3. So that's 4.06290, but I really only know that to the decimal point of 6. Then I'm going to add to 107. Now we're limited by decimal places. Okay, the product I knew to 2 decimal places. The value of 107 I know to 0 decimal places. So I am limited to 0 decimal places. So the answer there, 111.06, I know to 0 decimal places. So I'm going to drop the 0.06. The overall value I should report is 111. Okay, deep breath. This is our last section. Okay, successive operations. Let's do a more challenging one. Let's take the difference between these two numbers, 847.89 minus 847.73. Then we're going to multiply by 1.4673 times 10 to the fourth. If you put that into your calculator, you're going to get 2,347.68. First operation is subtraction in the parentheses. So we are limited by decimal places. Okay, the first number we know to 2 decimal places. The second number we know to 2 decimal places. Therefore, that difference we only know to 2 decimal places. So the 6 is our last sig fig. Now we're going to multiply. When we do multiplication, we are limited by whichever value has the least significant figures. The first one we know to 2. The second number we know to 5 sig figs. The least is 2. So this overall answer we only know to 2 significant figures. So start with the 2, the 3 is our last sig fig. Therefore, we're going to have to report this as 2.3 times 10 to the third. Moving the decimal there so you get the correct exponent on 10. So 2.3 times 10 to the third. 2 significant figures in that result. Final sections. When you're doing logarithms and exponents, how do you know sig figs? The rule for logarithms, you're going to take the log of a value. So let's just look at 6.00 times 10 to the negative fifth. You look at that value and ask how many sig figs are there in that value. In this case, there are 3. That's going to tell us, dictate, the number of decimal places we report the answer to. So if you put this in your calculator, you're going to get a value of negative 4.218. There are 3 sig figs in the value, original value. So I report my answer to 3 decimal places. So the 1 is the last significant digit, and I'm going to round up to 4.222. Okay, that's the rule for logs. The rule for anti-logs, which are exponents, it's the exact reverse. Okay, however many decimal places I know the exponent to, that's going to dictate how many sig figs are in the answer. Okay, it's the reverse of the above. So let's think about 10 raised to the exponent 12.5. The exponent 12.5 we know to 1 decimal place. Therefore, the result I'm going to know to 1 sig fig. So if you plug this value into your calculator, you get 3.16 times 10 to the 12th. And because there's only 1 decimal place in the exponent, I know this result to only 1 significant figure. So I would report this as 3, dropping the 0.16 times 10 to the 12th as my final value. So I hope this was a good review on significant figures. Just remember, practice, practice, practice. Work lots of problems from the assigned online homework. And if you need more practice, open your textbook to the questions at the end of the chapter and get more practice. Annie is demonstrating good concentration, so hopefully you can exercise the same in working lots of problems. Have a good one and thanks for listening. Bye-bye.